All right, so given the instructions will be saying, given the zeros, write a polynomial of least degree. So we go back to that idea that if we have 3 zeros, then what would be the highest exponent in the problem? X to the third. Okay, so that's what it means by least degree. Now, there are some exceptions to that we've got to take into account when you have certain kinds of zeros. So let's take this one that's an easy one to start off with. The zeros are 2, 3, and -1. Okay, so this goes back to the idea of working backwards from what we did when we were doing factoring out of that. So to build a polynomial, we want to start using the zeros to build the factors. So what would the factors be for 2, 3, and -1? X minus 2 and x plus 1. That would be the factored form of that polynomial. Remember, it's the opposite sign going there. So if it's just integers, you're going to start with those factors. And now we want to write the polynomial in standard form. So in standard form, that means multiply this thing all the way out. Okay? And because it's multiplication, it doesn't really matter what order you go in. You just need to pick 2 of them to start with, get the answer to that, and then multiply by the third one. I'm kind of a right to left kind of person. You may be a left to right kind of person. It doesn't matter. I don't care which way you do that. I'm going to do it this way. I'm going to put these 2 together first and then multiply that answer by x minus 2. It doesn't, like I said, it doesn't matter what order you start with there. So if I do these 2 together, that's going to be x squared plus x minus 3x minus 3. So that's just distributing x to the x plus 1 and then distributing a -3 to the x plus 1. And then I'm going to simplify that to be x squared minus 2x minus 3. Some of you may be able to do that, without the extra step in between. Just by doing that in your head, you've multiplied enough of those out over time. You've kind of figured it out. Okay. The last step would be just multiply x minus 2 times all of that and work that out. That's going to be x cubed minus 2x squared minus 3x minus 2x squared plus 4x plus 6. -2 times -3 is positive 6. And then simplify that to get your final answer, which is the polynomial x to the third minus 4x squared plus positive 1x plus 6. How can I tell if the polynomial I got at the end meets the conditions they gave me at the beginning? Highest exponent's 3 because I had 3 zeros. What other checks are there? Plug in the zeros into this for x, and I should get 0 for an answer, right? What's a quick way to check? Say that. Graph it, and it should be crossing the x-axis at what places? 2, 3, and -1. Okay, so once you get the polynomial, if all of your zeros are real solutions, you should be able to look at the graph and see it across the x-axis at those spots. Okay, so building a polynomial, multiplying a polynomial out and getting it into standard form. That's what our job is. So that's very simple to do. Let's look at example B. And let's say we have zeros, spell zeros, 3, 4, and -3. What would be our factors? Good. Those are the factors. Opposite signs, again, you got integer values, you're just going to change the sign. That's all you really have to do. Now, the next thing is to multiply it all together, and this one has some shortcuts to it. Does anybody see one? Okay. We got a difference of squares in there. That's right. We've got x plus 3 and x minus 3. Those are the factors to a difference of squares. So if I just rearrange this so that the x minus 4 is in front and think about it in this way. I really don't have to rewrite it like that, but if I think about putting the x minus 3 and the x plus 3 together, the multiplication for that is quicker than x minus 3 times x minus 4, right? Because these two are going to multiply together to be x squared minus 9, right? And there's a shortcut because we know it's a difference of squares to get those particular factors. And then we would multiply x minus 4 times that x squared minus 9. So that'd be x cubed minus 4x squared minus 9x plus 36. And there's our polynomial. And again, we can check that. Got the degree of 3. We had 3 zeros to that thing. We see it. We could plug those in, get 0 as a result, or we could graph it and see it crossing the x-axis at all 3 of those places. So there are checks to be able to make sure that that's happening. So that's nice. That's going on. Example C, zeros of 0, -2, and 7. Again, it's integer values for our zeros, so that makes our factors easy. What are our factors? X plus 2, x minus 7. So we get the x for the 0, because remember we said our factors equal to 0 to get the solutions. So only way to get 0 is just to set plain x equal to 0. So that's where that's coming from. And then you just multiply this stuff out. If I multiply these two out together, that's going to be x squared minus 5x minus 14. And that's just doing that middle step in my head. Set -7x and positive 2x is -5x. That's where that's coming from. And then distribute the x to everybody. X cubed minus 5x squared minus 14x. And we've built a polynomial of least degree that has those particular zeros. Here's the reason they say build a polynomial of least degree. That's not the only polynomial that has those zeros. There's actually an infinite number of polynomials that have those particular zeros. We're building one of least degree that has those zeros, and we could manipulate this and make a bunch of different ones that had that. But we want the easiest one is what we're trying to build. Because we want the most simplistic. We don't know which one it was to begin with, but we're just trying to work backwards here. All right. Now, what if you had fractions as zeros? And that kind of complicates the factors a little bit. So let's say we had a -1, a 2/3, and a 5 out of that. So building the factors for that is a little bit more difficult, but once you see how it works, it's not too hard. It's just kind of a memorized thing there. So what's the factor for the -1? X plus 1. You all got that. What's the factor for the 5? X minus 5. We know those. The 2/3. 3x minus 2. Good job. The denominator is going to be your number in front of x. The opposite of the numerator is going to be your other part. Okay? That's always what it's going to be there. So denominator is going to be what's in front of your variable, and then the numerator, the opposite of it, is the other part out of that. Because you think, okay, if I solve 3x minus 2, I'm going to get 2/3 when I set that equal to 0. And then you're just going to multiply all that stuff out again. For this one, I'm going to do these two together first, just because that's quick. I can do that pretty fast. That's x squared minus 4x minus 5. And again, it doesn't matter what order you go in. It's just going to change kind of what your middle step looks like, but you can multiply any two of them together first, whichever ones you think looks the easiest. And then I'm going to multiply 3x minus 2 to that trinomial that's there. and work that out. So that's going to be 3x cubed minus 12x squared minus 15x minus 2x squared plus 8x plus 10. And then I'm just simplifying that. 3x cubed minus 14x squared minus 7x plus 10. So putting that fraction in there just makes you have a factor that's a little bit different out of that. The reason we want to write it as 3x minus 2 and not x minus 2/3 is because if we throw that fraction in there, it's going to make our coefficients not be integers, and we want a polynomial with integer coefficients. That's what standard form means. How about that? So, all right, let's talk about the next thing, and that's this thing called conjugate pairs. And conjugate pairs is if a radical, also called an irrational number, a radical or irrational zero exists for a polynomial, then its conjugate is also a zero. Example is probably the easiest way to show you this. Okay, so they tell us to build a polynomial of least degree, the same instructions, and they tell us that 5 is a zero and that the square root of 2 is a zero, and then that's all they tell us. What they didn't tell us is what we're knowing from this conjugate pairs. It's actually a theorem in algebra. The conjugate pairs theorem tells us that if square root of 2, that's an irrational number, it's a radical. If it's a zero, then its conjugate is a zero. The conjugate just means the opposite sign in the middle. So negative square root of 2 is also, and they don't tell us about that, so they didn't give this one to us. We've got to know that it's there. What that creates is 3 factors for this, so we should end up with a cubic at the end. So our factors are x minus 5, x minus the square root of 2, and then x plus the square root of 2. The factors have the irrational part in there. We're going to see the same thing happening if we have complex solutions as well. Because remember, where do those come from? They come from solving a quadratic either by square roots or quadratic formula, and there's always that plus or minus that's in the middle of that. That's where that's coming from. All right, so which two would you think would be the best ones to multiply together first? The ones with the square roots, because that's really the factors of a difference of squares, really, that's there. And it makes here's what's going to happen. Anytime you multiply those conjugate factors together, that square root's going to go away. If there's a complex in there, the I is going to go away, and we're going to have to we'll take care of those things. So if I multiply these two together, it's going to be x squared plus x square root of 2 minus x square root of 2 minus the square root of 4. And we can simplify that. X minus 5 is still out there. To be x squared. And then these two pieces in the middle cancel out. And what's the square root of 4? 2. And now we've got something a little easier to multiply together. X times x squared is x cubed minus 5x squared minus 2x plus 10. And again, you can still check that using the graph. we should be able to see it crossing the x-axis at 5, and then we could check square root of 2. We'd see it crossing at that weird decimal place, but we could check that with the calculator as well. So conjugate pairs, always going to have the opposite. If you've got a square root in there, you're going to have the opposite with it too. Let's look at this one. The zeros that they tell us about are 4 and 1 minus the square root of 5. What's the one that they didn't tell us about? 1 plus the square root of 5. That's the conjugate for 1 minus the square root of 5. And the factors are a little bit more difficult to deal with here in multiplying, but you're always just going to change the sign in the middle for that conjugate out of that. So we got x minus 4. That's the one everybody knows. And then the other ones, it's always going to be x and then minus 1 minus the square root of 5, and then x minus 1 plus the square root of 5. If you'll just do it that way, it'll take care of the signs for you. Use a minus sign there. And then multiplying out the ones with the square roots, it's a little long here because there's 3 pieces in each one. So that makes a longer multiplication. But understand that when you get done with that part, the square root part should go away. If it doesn't, then you've mismultiplied somewhere or maybe just misadded somewhere. Okay, so the square root part should go away once we finish this. So we're going to multiply x times all of that. So that's going to give me x squared minus x plus x square root of 5. And then I'm going to multiply -1 times all of that. So that's going to be negative x, and it might help me to stack this up. Negative x, positive 1, and then negative square root of 5. And then I'm going to multiply everybody by the negative square root of 5. So I'm just using a different color there. So negative square root of x, or negative x square root of 5, that's what I meant to say. And then positive square root of 5. And then negative square root of 25. All of this stuff is the conjugate pairs multiplied together. Then you look at canceling stuff out and putting stuff together. So I got x squared. I got negative 2x. These guys cancel each other out. These guys cancel each other out. And I end up with negative square root of 25 and a positive 1 together. What's the square root of 25? 5. So 1 minus 5 would be minus 4. And I've got the x minus 4 that I got to multiply out to that, because this turns into 5. That's what's happening to get that 4. Positive 1 and negative 5. It's a minus 4. And then we're just multiplying the last part together. The x cubed minus 2x squared minus 4x minus 4x squared plus 8x plus 16. Simplify that. X cubed minus 6x squared plus 4x plus 16. Oops. 16. So a little bit long and a lot of operations involved, but it's still not impossible to do. I mean, it just takes paying close attention to what you're doing. Let's throw a complex in there. Here are zeros. Let's say we had negative 1/5, 3, and 6 plus 5i. What did they not tell me about? 6 minus 5i. All right. So we've got 4 factors here that we're going to build. So that should mean that we end up with x to what power at the end? x to the 4th. Okay, so give yourself plenty of room. What's the factor for the negative 1/5? 5x plus 1. Good job. What's the factor for the 3? X minus 3. So those are my regular ones that, maybe I want to do those together in a little bit. And then I've got x minus 6 plus 5i, x minus 6 minus 5i. If that were a negative number in the front there, they would change that to x plus the two pieces, the two conjugates, okay? Now, let's multiply the conjugates with the i's involved. That's going to be the toughest part here. This is the hardest thing in this particular topic, is to put these two together. If you'll take your time and just do one piece at a time, that you're going to be fine. So x times everything, so that's going to give me x squared minus 6x minus 5ix. And then I multiply negative 6 times everything, which is going to give me another negative 6x. That'll be a positive 36 and a positive 30i. And then multiply 5i times everything. That'd be positive 5ix, a negative 30i, and then I have negative 25i squared. So this is going to go back to you remembering how we did all those things with complex numbers a while back. So most everything's going to simplify up pretty nice there. You've got x squared, you got a negative 12x, negative 5ix, and positive 5ix cancel each other out. Remember, the I part or the square root part should go away at the end of that multiplication that you're doing. Okay, if it doesn't, something went wrong. Okay, and then the positive 30i and the negative 30i, they cancel each other out. And then we got this positive 36, and then we got a minus 25i squared. What does I squared equal? Negative 1. So this part is going to turn into plus 25. Negative 1 is I squared, so negative 25 times negative 1 is positive 25. So that's why I'm changing that to a plus 25. 36 plus 25 would be 61. Is that right? 56 plus 5, yeah. So that ugly stuff that's in the brackets there turns out to be this nice little trinomial. It should end up being a trinomial when you get done with that part. If it's not, something went wrong. Okay? Let's go ahead and multiply these two together, because that's just normal multiplication. Been doing that since junior high. So 5x times x is 5x squared minus 15x plus 1x minus 3, and so that simplifies to be 5x squared minus 14x minus 3. Now I just have to multiply these two trinomials together. Again, this is a long process, but none of the math is just extremely crazy. It's all things we've done before. 5x times x squared, 5x to the 4th. And then 5x times negative 12x would be negative 60x to the 3rd. And then 61 times 5 would be 305 x squared. And then multiply everything by negative 14x. So that'd be negative 14x to the 3rd. 14 times 12. 144 plus 12 more plus, so it'll be 178. Is that right? 168. 168. Yeah, an extra 10 in there somewhere. X squared, and then 14 times 61. Everybody knows there's 61's times tables, right? 854. Big numbers, but that's still not enough to live off of anyway. and then multiply everything by -3. So that's going to be a -3x squared. A little easier numbers here. That's got an x. That 854 has got an x on it. Positive 36x, and then 3 times 61 would be 183. And last step, just write it out. Remember, we said we would have a fourth power, so 5x to the fourth is right. -74x cubed. 305 and 168 be 473. Minus 3 is 470. X squared. 880, 890. And then minus 183. Again, checking that with plugging those numbers in, or doing synthetic division if you wanted to with any of the zeros that were listed above. That would be a good way to check that. It works out pretty easy. All right. Not the funnest thing in the world, but not the hardest thing we've ever done either. Okay, so it's a good way to end up polynomials, just being able to take information and build a polynomial based on that. Again, this is not the only polynomial that would have those zeros, but it is the smallest polynomial that would have those zeros. Another polynomial that would have that is if you double everything, 10, -148, keep going, double everything. It would still have the same zeros, but there would be a GCS in there that you would take out. All right. So now, when you, I'm just going to pass this out. I'm going to talk about it. Most of these are the normal kind, which is regular numbers in them, not the conjugates. When everybody get one of these, we're going to talk about the ones that have that multiplicity. You know what to do with that, but make sure. Got an extra. No line. This though. All right. When you look at like number 6 there, number 8, they've got that multiplicity 2, MULT 2. What does that mean about -1/3? It's a factor twice. So you would have 3x plus 1. Technically, you could write it as squared, or you could write it out 3x plus 1, 3x plus 1, like that. And then the other factor is 5x minus 2. All right. Did I read that right? Yeah. So this would be the either way of writing the factored form for number 6. Multiplicity, whatever it says after it, MULT, and then the number tells you how many times that's a factor. If it doesn't have MULT with a number after it, then it only counts once. That's how that goes. All right. But that's your practice for this. And so you've got about 40 minutes left in class to work on that. 2 minutes problem to get. And if you don't get it done, I don't say this very often, it's homework. Not going to have a work day tomorrow. Okay, so you need to work today and try to get as much of that done as you can. And we'll go from there. Okay, so tomorrow we will